right, folks, we now want to talk about impulse and describe what it is, how it relates to momentum, and do a few examples. So, first things first, Newton's second law, as it's most usually written, looks something like this, right? Where we say that F net equals mass times acceleration. However, this is not the most general way to describe forces. Okay? Um, so, what we mean by this is acceleration is equal to change in velocity over time. So I can just replace A with delta V delta T, right? However, the reason that this is not the most general way to write this is, what if the mass can change? Okay? What if by applying a force to an object the mass changes? Then we would have something like this. Make that a bit of a sharper arrow. Then we would move the delta outside of the MV, and we would obtain something like this. Okay? And so this is actually what a force is. Okay? This is the best definition of force. Well, we're almost there. Anyway, we define the momentum of an object to be its instantaneous mass times its velocity. So, when you apply a force to an object, what you see is that it's a change in P. And if we let our time intervals be small enough, then this becomes the derivative. Okay? So this is Newton's second law reformulated to include the possibility that the mass can change. Okay? And when that happens, we say that your force, your net force, doesn't just cause an acceleration, but it causes a change in momentum. Okay? It causes a change in momentum. And so, in words, okay, forces cause changes in momentum. This is one of the most fundamental ideas in all of physics. Okay. So with that, we can actually recast Newton's laws in terms of momentum, and they actually become a little bit more compact now. So the first law, which generally says an object at rest will stay at rest and an object in motion will stay in motion unless acted upon by an external net force, we can actually summarize all of that very, very briefly object momentum is constant. Absent external net external forces. Okay, so an object's momentum is constant minus or when no external forces are present. So this is a much more compact way of writing out the first law. The second law actually becomes even shorter yet. Net external forces cause changes in momentum. Now, let's contrast this with the general way of stating Newton's laws before, particularly Newton's second law, which goes something like this. When an external force is applied to an object, it will accelerate, and it will accelerate such that the acceleration is in the same direction as the impressed force, and it is inversely proportional to the mass. That is a mouthful. That is a lot of words. Once you understand them, they make a lot of sense, but here all we have to say is that the net external force causes changes in momentum, and by virtue of this word, changes, we can actually see everything in the language that's in the original formulation. So the whole idea that the acceleration is in the same direction as the impressed force comes from the vector nature of things. So the fact that momentum is a vector and that forces are vectors, this equation is telling you exactly that. Whatever direction F net is, that must be the same direction that your momentum is changing. It's not the direction of your momentum, it's the direction your momentum is changing. Okay? Now, mass is not explicitly here, although it is in here. Okay? But the biggest idea, the force being in the direction of the impressed, or the change in momentum being in the direction of the impressed force, is directly implied by the vectors. Okay, so that's why we don't have to explicitly state it in this form, because the fact that these are vectors and we know what the word change means, in derivative form it's dp dt instead of delta, but it doesn't matter. Okay. We can still see that F and dp are going to be in the same direction. The third law actually really doesn't change. Okay. If there are two objects exerting forces on each other, object 1 exerts force F1 on object 2, object 2 exerts force F2 on object 1, then these forces must be equal and opposite, right? So the third law doesn't really change. However, we will see that there's a direct connection between this and the conservation of momentum. Okay, but that's not the point of this video. The point of this video is impulse. So what does everything I've said so far have to do with this idea of impulse? Okay, so here it is. This is Newton's second law. And for the rest of the video, I might drop the net and just leave it as being implied, just because it's a little tedious to keep writing it over and over and over and over again. But in any case, okay. there's something I can do here, and that thing is I can multiply both sides by dt. Okay. So now what this equation is telling you is that your force applied over an infinitesimal time gives you an infinitesimal change in your momentum. But if you go for a full time interval, some finite time interval, then you have to integrate this. Okay, so the left-hand side is going to be integrated from whatever your initial time is. Most of the time that'll be 0 to some final time. And the right-hand side, you can automatically do the integral because the integral of dp is just p, but this is going to be evaluated from whatever the initial momentum was at time 0 to whatever your final momentum is at time final. And as I just mentioned, the integral of dp is just p evaluated between these 2 points, or 2 values, I should say. And so then that just becomes p final minus p initial, which is just delta p. Okay? Now, this left-hand side, this is what we define as impulse. And it gets the letter J. Okay, so this represents the area under a force versus time curve. So if I have a force as a function of time, okay, and for the moment, let's just say the force is constant. Okay, so let's let F be, I don't know, 60 newtons. Why not? And let's say that our time interval is 10 seconds. Why not? Right? And we'll let T0 be 0. So we're going to start our stopwatch from 0. So I'm going to start here at the origin and go to 10 seconds. And I'm going to apply a force to an object for at 60 newtons for that time interval. And it's constant. Okay? What this is telling you, this is the area under your F versus T curve. So first things first, impulse is equal to the area under your force times time curve. Okay, force versus time, I really should say. And so in this case, it's really, really easy to compute. It's just this area right here. Okay, so this area is going to have a width of 10 seconds and a height of 60 newtons. So this gets 600 Newton seconds. I really shouldn't have that 0 there. That's fine. Okay, 600 Newton seconds. But now Newton seconds, if I break newtons down into its base units, kilograms times meters per second squared times seconds, this becomes kilograms times meters per second. But this is the units of mass times velocity, or the units of momentum. Which it must, because it equals the change in momentum. And the units on a change are equal to the units of the thing. Whether it's change in position, change in velocity, change in momentum, it doesn't matter. Okay, so your impulse is your area under your F versus T curve, right? And when your forces are constant, you're just going to take the area of a rectangle. That's all you need to do. Okay. But let's do a slightly more sophisticated example, right? What if my force is a linear function? Okay. Ooh, no. Whoops, I'm missing something. If it starts from rest. Okay, so we know nothing about the object. We just know that a linear force, a force that's time dependent, is going to be acting on it. Okay, and we also know that we know the slope. We know the slope is 2, and we know the intercept is 0.5. I'm going to tack on a part B here. And that is, what are the units of A and B? Okay. So we'll actually do B first, and then we'll do A. So if my force is equal to AT plus B, this side has to be newtons, and therefore A has to be newtons, or A has to be whatever will cancel out with T to give you newtons. And so the units there will be newtons per second. Okay. So the units on A have to be newtons per second to cancel out the seconds from T. And B, likewise, just has to be newtons from the get-go. Okay. So the units on A are newtons per second, and the units on B is just newtons. Okay. Now we'll do part A. Okay. So we're not told to start our stopwatch at 0, but we might as well. So if I start my stopwatch at 0, let's get rid of that almost minus sign looking thing. So I'm going to start at 0.5, and my slope is 2, so there's 5 ticks here, so it would be about 1, 2, 3, 4. So I'm going to start right here at this point, and then I'm going to go up 2. Okay. For every second. So this is 1, this is 2. I might not have enough space here. We'll see, but you'll get the idea. Yeah, I need more space for that, or I just need to change the scale. It doesn't really matter. We will, if you'll allow me, we'll just fudge it. Okay, and we'll just claim that this is the 0.20, just for the sake of example. So that means I'm going to start here, and then I'm going to end up here, and I'm going to have my force would represent that function right there. Okay. So now the change in momentum represents the area under this curve. Okay. And so to find the final momentum, we recognize that F dt is equal to delta P. Okay? And delta P is, of course, P final minus P initial. But if we start from rest, then P initial is 0. And so to find P final, all I have to do is actually take this integral. So this is going to be from 0 to 5 of 2t plus 0.5. Whoops. And I'm dropping the units for brevity's sake. So when I integrate this, this is going to be t squared plus 0.5t evaluated from 0 to 5. So this is going to be equal to 5 squared plus 0.5 times 5. So this is going to be 25 plus 2.5. But the units are indeed going to be kilograms times meters per second. Okay, so the final momentum is found from something like this, right? So what about a more sophisticated example? Okay, so think of a bat hitting a ball. if I think of a bat hitting a ball, um, before the ball and the bat are in contact, there is no force. And the force will start to be exerted on the ball. Think of the force exerted on the ball by the bat. The force will be exerted on the ball the instant that they make contact. But because the bat is swinging through, it will compress the ball as the bat is swinging into the ball, trying to change its direction. And the ball in turn is compressed extremely highly. Okay, it's highly compressed, let's put it that way. And then, after the point of maximum compression, the ball will start to release from the bat, and then it'll leave the bat, and eventually the force goes back down to zero. So, in this case, the force will start at zero right at the time the ball is contacted, and it'll go back down to zero at the point that the ball releases from the bat. But in between, it'll reach a peak. So I need a function that will describe going to zero at 2 points, but then having a peak somewhere. And if you think about it, this should make a lot of sense. To a really good approximation, hitting a ball with a bat is going to be a somewhat symmetric thing. As the ball is compressed initially by the bat, it's going to uncompress essentially the same way. So the force function before the peak is going to match the force function after the peak pretty closely. Now, this is not universally true for every forces, but for a bat hitting a ball, it's a very reasonable thing to conclude. So what we can say is, if nothing else, our force function might look something like this, right? It'll start out at zero, it'll reach a peak, and then it'll come back down, and it'll be pretty much symmetric. So at this point, you actually would need to go into a laboratory and get measurements for velocities and things like that during the collision to actually really do a good job trying to fit exactly what function works best. However, there is a class of functions that, to a really good first approximation, you can model this relatively easily. And that is with a sine squared function. Okay? Now, bear with me real quick. Okay? A typical sine function looks something like this. Now, we're not going to be worried about a phase shift or anything like that, but to break this down, this is saying the position of a sine wave is equal to its amplitude times the sine of the quantity omega t, where omega is your angular frequency, and t is your time. Okay? So your angular frequency is going to have units of radians per second. And because radians is a unitless number, radians per second times the seconds you get from your time just goes to radians, which is what the sine function wants. Okay. So what you would need is so let's say that there's individual data points here that you have then fit this particular sine function to. Okay. And so you're basically trying to parameter estimate from your model fitting to your data. Okay. So your amplitude, in our case, represents the maximum force. Okay. So our model actually, so let me write it like this. Our model, if I want to write this as sine squared, so then this would be a times sine squared omega t. And you might be thinking, but wait a minute, why not square the a? Well, a is just a number. It's an amplitude. So an amplitude squared is still just a number, so we might as well still just call it a. Okay. But in any case, so now the question is what to do with omega and how do I do all of this? Okay. So we need the experimental data. Now, I don't have experimental data on hand, but we can estimate some things. Okay. So, one very common thing to do here is to use your data to estimate F max. Okay. So we're going to use data to estimate F max. Now I'm going to pull this data, kind of out of thin air, but it's actually reasonable data. So a typical collision in Major League Baseball between a bat and a ball, it's going to be on the order of about 8 thousandths of a second. Okay, not 8 thousandths, but 8 10 thousandths. Excuse me, of a second. And you can even look that up. It's really really short how long these time intervals are. And a baseball has a mass of about 0.145 kilograms. And incoming speeds, if you're in the major leagues and a major league is pitching at you, 90 to 100 mile an hour, that's, like 40 to up to about 48 meters per second. So let's say V initial is, let's just make it a nice number. Let's just say 40 meters per second. So what we want to do is use this idea of impulse to estimate F max. Okay. And so what we want to do now is assume rebound velocity is equal to initial velocity in opposite direction. This is actually a bad assumption. Bats have a very special property, bats and clubs, in that typically the external, what's the word I'm looking for? The outgoing velocity is larger than the incoming velocity. So typically bats impart more energy to the ball than they had before, and so they leave with a higher exit velocity. That's what I was looking for. They leave with a higher exit velocity than an initial velocity. But for our purposes here, we'll just assume they're in equal but in opposite directions. So if I have a batter, and this is going to be really bad, but They have a bat. Imagine that's a bat. It almost looks like a cricket bat, but this is a major league bat, right? So our baseball is coming in, and after the collision with the bat, it leaves with the same velocity in the opposite direction. So I need to define a coordinate system. So let's let the exit velocity be plus x. And that means that this is going to be minus 40 meters per second. And this is going to be plus 40 meters per second. So automatically we can calculate what delta P is going to be. Okay, so this turns into 0.145 kilograms times 80 meters per second. Okay, and that turns into, pull out my calculator real quick. .145 times 80. Okay, so our change in momentum is 11.6. But remember, your change in momentum also equals your impulse. Okay? Change in momentum equals impulse. So we can automatically say that our impulse is 11.6 kilograms times meters per second. Okay, fair enough. Whoops. So now what we need to do is recognize this, okay? And remember, we're looking for the max force. We want to estimate the maximum force, but F max is the amplitude, right? So F of t can be written as F max times sine of omega t. But so now, what do we do with omega? Well, notice, once again, that our function has to go from 0 back to 0. So if I plug in 0 for t into my wave function, I'm going to get 0, and by extension the sine squared, I'm going to get 0. But when is the next time that this goes to 0, right? So we have to use the ideas from trig that sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0. And so the general form is the sine of n pi equals 0 with n equal to 0 plus or minus 1 plus or minus 2, etc. Okay? So the very next 0 in this function happens when omega t equals pi. Okay? And that comes from right here. My first 0 is when omega t equals 0, and my second one comes from when omega t equals pi. Okay? So what that means is omega t has to equal pi. And so at that point, I know what my time interval is. T0 is 0, T final is 0.008, 0.0008, and therefore my omega has to be pi divided by my final time, which is pi divided by 0.0008 seconds. And by the way, pi has units of radians. And so now we plug that into our calculator. And we're going to get pi divided by 0.0008. And so my omega is 3,926.99. I'm going to write that down as 3,927 radians per second. Okay. So now the function that we have to integrate looks like this. Okay, so this is the full-blown thing. So we need to integrate this function. Now, what I would do is pull Fmax out front, and then when I integrate this, there we go. I can pull Fmax out because it's constant, right? It's just the peak of the graph, so it's just a number. And then we just need to integrate this sine squared function. Now at this point, I would recommend using a computer, okay? However, there is a neat trick that you can do, all right? But first, let's plug it into Wolfram Alpha and see what we get. So if I tell Wolfram Alpha, integrate sine squared of 3,927 times t from 0 to 0.0008, I get 0.00039999 repeating. Oop. You'll notice that this is suspiciously close to 0.0004, which is 1/2 of our t final. Okay, so this is actually a property of the sine squared function because sine squared x plus cosine squared of the same x equals 1, right? This contributes 1/2, this contributes 1/2. So in terms of an integral, okay, if I go from 0 to t final, right, then because all of this is 1 anyway, this essentially becomes the integral of 0 to tf. This really should be over x. Um, Mixing up my x's and t's, not really a good thing. Okay, so this just becomes xf, but when I only have one of these, this is 1/2. And so then that gets pulled out front, and the integral of dx from 0 to xf is xf. So we get 1/2 of whatever your upper limit is if your lower limit is 0. So we can then say that f max times 0.0004 has to be equal to 11.6 kilograms times meters per second. And so now we can find f max by taking 11.6 and dividing by 0.0004, which is 29,000. 29,000 newtons. So your baseball in a major league setting is going to experience on the order of 30,000 newtons when it's hit. And that might seem extreme, and it is, but it's really because of the way the ball is designed to rebound off the bat. It comes off the bat at a larger speed instead of losing speed, right? Which is really phenomenal. So when you're hitting a baseball with a bat, a softball with a bat, a golf ball with a club, you can generate phenomenally large forces compared to the typical forces that a human will exert when they're pushing things around or lifting things, right? So, this is a basic connection to how forces connect to momentum and what the definition of impulse is. Now, I will mention one thing, and let me come back up here, okay? Look at this form of Newton's law, okay? What this is telling you, well, actually, let's use not this form, but this form. When you move away from derivatives and you go to deltas, then this becomes your average force that was exerted. So that would be like the equivalent of what force would give me the same area under the curve. Right, so there's the area under my original curve. And so then F average is the force that exerted over the same time interval those areas would be equal, right? Those shaded areas would be equal. And so what you'll notice here is that for a given change in momentum, F depends on delta t. So if you know what the change in momentum of your object or system is, the forces that are acting on it, their strength will be determined by delta t. For very short delta t's, result in large forces. So if your change in momentum occurs over a very short time span, then you get very large forces. If, however, longer delta t's, smaller forces. And one practical area where this occurs is if you've ever driven on the interstate or a state highway and have seen like water barrels or sandbags at specific points, those are points that have had typically higher than average across other parts of the road collisions, people sliding off the road and colliding into concrete structures or into mountainsides or whatever. And so the idea of putting like water barrels in front of, concrete pillars at an overpass, say, the whole idea is that if a car loses control on the road, they swerve off into the grass and they hit the pillars at really, really high speed, your change in momentum changed very, very rapidly, right? Your momentum changed over a very, very short time interval. I could be going 70 miles per hour, and then in, maybe a hundredth of a second later, my speed is 0 miles per hour. That's a very abrupt change, okay? Whereas if I can extend that and go from, say, 70 miles per hour to 0 miles per hour, but over a much longer time interval, maybe this time it's up to half a second or so. Now look at this. I've increased my time by a factor of 50, and therefore I will decrease the average force felt by the car and the occupants in the car by a factor of 50. Okay? So the longer you can make your collisions last, the longer you can make your changes in momentum last, the smaller the average force. So this is why you want things that can compress and take more time, because the more time, the lower the force will be. Okay, so that's a very, very important consequence. So to wrap up, right, momentum is equal to mv. Your impulse is equal to your integral of your force over your time, and it is also equal to your change in momentum. Okay? So these are the equations that you want to keep with you moving forward. All right? I hope that helps. I hope this is a useful video, and we will see you next time.